Ladies and gentlemen, welcome back to lesson 18 in group theory. In the next 4 lessons, I'll be giving you some isomorphism theorems. I'll be labeling them the first, second, third, and the fourth isomorphism theorems. But I would say that the first isomorphism theorem, which is the lesson of today, is the most important one by far. It has the most number of applications that we're going to see in the future. We're going to be stating this theorem and we're going to be proving it. And then afterwards, I'm going to give 2 examples using the isomorphism theorems. Let's get started. Let us start by stating the first isomorphism theorem. Let G and H be 2 groups, and let phi be a homomorphism going from G to H. Then the theorem says that the kernel of phi is a normal subgroup of G, which invites the next statement, which says that the quotient group G by kernel phi is isomorphic to the image of phi. Let's get down to the proof. The first part of the proof has already been done in lesson 14.1, where we said that the kernels of homomorphisms are all normal subgroups, and normal subgroups are all kernels of some homomorphisms. The second part of the proof, we would like to find an isomorphism, therefore saying that the quotient group G by kernel of phi is isomorphic to the image of phi. And this isomorphism is going to be given very naturally. We're going to be defining a map, psi, that takes an element from the quotient group. Notice that I can say this is a group because the kernel of phi is now a normal subgroup of G. So psi takes an element from this group and gives an element in the image of phi. And it is defined to be taking a coset of kernel of phi, G ker phi, and giving back the image of G by the homomorphism phi stated in the theorem. And this is the definition of psi. The first thing to check is that psi is a well-defined map. It is well-defined because if we have 2 cosets G1 ker phi and G2 ker phi are equal, then by definition of equal cosets, we have that G2 inverse G1 is an element in ker phi. If it's an element in ker phi, then if we apply phi on this element, we should get back the identity element. And so, because phi is a homomorphism, we can split this up into the inverse of phi of G2 times phi of G1. And this implies that phi of G1 is equal to phi of G2. Therefore, we've said that if 2 elements in the domain are equal, then their image is also equal. This is just psi of G1 ker phi is equal to psi of G2 ker phi. So psi is a well-defined map. The next thing to check is that psi is a homomorphism. This is a very straightforward check because psi of 2 elements G1 ker phi, G2 ker phi is equal to psi of G1, G2 ker phi. This is by definition of coset multiplication. But G1, G2 ker phi, when we take psi of that, this is equal to, by definition of psi, phi of G1, G2. But phi is a homomorphism, so this is equal to phi of G1 times phi of G2. And phi of G1 is equal to the image of the coset G1 ker phi by psi. And phi of G2 is also the image of the coset G2 ker phi by psi. Thus we have that psi of 2 elements is equal to psi of the first element times psi of the second element. Therefore, psi is a homomorphism. We would like to confirm now that psi is an injective map by confirming that the kernel of psi contains only the identity element. Just a reminder that psi takes an element from the quotient group and gives an element in the image of phi. It takes a coset of kernel of phi and gives you phi of g. So, if you want to show that the kernel of psi contains only the identity element, we want to see what happens if a coset, g ker phi, lies in the kernel of psi. This is true if and only if, by definition of the kernel, psi of the coset gives back the identity element in the image of phi, which is just the identity of g. Now, what is the definition of psi? So this is equal to, by definition, phi of g. So we can say this is if and only if phi of g is equal to the identity. But phi of g giving the identity means that g has to be an element of the kernel of phi. Okay, notice this is phi this time. And because g is an element in the kernel of phi, this is true if and only if the coset g ker phi is none other than the trivial coset, the identity coset, ker phi. So if g ker phi is none other than the identity coset, and it has been taken for any coset g ker phi, then this means that ker of psi contains none other than the identity coset, which is ker psi. And since it contains nothing but that, this means that psi is injective. Next, we would like to see that psi is surjective. That means every element in the image of psi is mapped to by some element in the domain of psi. So now we need to see a random element in the image of phi. Let k be an element in the image of phi. Then, because k is in the image of phi, it is mapped to by some element in g. K is equal to phi of g for some element g in g, because it is in the image of phi. Then we have that k is equal to phi of g. But what is phi of g equal to? Well, phi of g is exactly defined to be the image of some g ker phi by psi. So this is equal to psi of some coset g ker phi for some element g in g. And this very well lies in the image of psi. So psi is surjective. So we just succeeded in constructing a well-defined map that is a homomorphism that is both injective and surjective. This means that psi is an isomorphism. An isomorphism between the two groups g ker phi and the image of phi. So this means that the two groups are isomorphic. Completing the proof of the first isomorphism theorem. Let us now consider an example in the dihedral group D2N. We have the normal subgroup, which is the subgroup generated by the rotations R. This is a normal subgroup of D2N as we've previously seen in lesson 14. We consider now the homomorphism taking an element from the dihedral group D2N and giving us an element in the subgroup generated by S. Remember, the subgroup generated by S is simply the cyclic group of two elements, 1 and S. So since all of the elements of the dihedral group are in the form r to the k or s r to the k, we will just define the phi on where it will send these two variants. We define phi to be sending r to the k to the identity element and sr to the k to the element s. And phi is a homomorphism, and I will leave that to you as an exercise. So we have that the image of phi is by definition the entire cyclic subgroup generated by S. The kernel of phi is all of the elements that phi map to the identity, and in this case it is all of the powers of R, and since it's all of the powers of R, we can say it's the subgroup generated by R. So by the first isomorphism theorem, recall that if we take the group and we take it the quotient group with the kernel of phi, this is isomorphic to the image of phi. And the kernel of phi is just the subgroup generated by R. The image of phi is the subgroup generated by S, and this is what we have as a result. This quotient group is isomorphic to this cyclic group of order 2. In particular, if you would like to know the index of the subgroup generated by R, by Lagrange's theorem, this is equal to the order of the quotient group D to N by R. And because these two groups are isomorphic, in particular, we have that the order of these two groups are equal. So this order is equal to the order of this subgroup generated by S, which is equal to 2, because there are only two elements in that, 1 and S. So just by using Lagrange's theorem and the first isomorphism theorem, we've succeeded in calculating the order of this quotient group. If this example sounds familiar to you, it is because we've already encountered it in lesson 14, but this time we have not had to explicitly count all of the elements in this quotient group. Consider now the example of the group of integers. We fix a natural number n, and we consider a map phi taking an integer k and giving us k modulo n. So an element from the integers to an element of z and z. Phi is a homomorphism, and I leave that to you as an exercise. Phi is surjective, and I also leave that to you as an exercise. And so the image of phi is the entire codomain z and z. Let us now calculate the kernel of phi. The kernel of phi contains all of the elements that phi map to the identity. What is the identity in z and z? Well, the identity in z and z is 0 bar. What kind of elements are mapped to 0 bar? Well, those are exactly the multiples of n. If we had, for example, z12z, so the clock, then the elements that will map to 0 bar are all the multiples of 12, 0, 12, 24, 36, etc. Even the negative numbers are mapped to 0 bar. So it is going to be denoted by n times z. This is simply the multiples of n. And notice, because z is an abelian group, all of its subgroups are normal. So this is a normal subgroup. By the first isomorphism theorem, we have that the group Z quotient with the normal subgroup ker of phi is isomorphic to the image of phi. What is the curve phi? It is nz. And what is the image? It is said to be all of z and z. It seems a bit silly to say that z and z is isomorphic to z and z, but this is important to notice the distinction here that nz here acts as the kernel of phi, while z and z is the group, which is coincidentally the image of phi in this case. Before finishing this lesson, I'd like to give the intuitive side of the first isomorphism theorem. Like I said, if we have a homomorphism, this is a map that respects the structures of both groups. This homomorphism is not necessarily injective nor surjective. So what we want to do is we want to make it injective and surjective by changing some stuff. How do we make this map surjective? Well, the most obvious thing to do is change the codomain so that it's smaller, so that it contains only the elements that phi is mapping to. So this is the image of phi. Now it is surjective because the image of phi contains only the elements that phi maps some element to. But phi is not necessarily injective. So how do we make it injective? Well, remember, injective means that the identity element here is mapped to only by the identity element here, not by some other element g that is not the identity. So what if I have g1, g2, g3? All of these elements map to the identity. I don't really want several elements. I just want one element, which is the identity, mapping to the identity. The answer here is to collapse all of the elements that map to the identity into a single element, which we call ker phi. And this element is the identity coset in G ker phi. And we have already seen in lesson 14 that when we collapse things in the quotient group, we preserve the same structure. We have a group with the operation that is induced from the original group operation. So this process of collapsing essentially preserves structure of G. So not only do we preserve the structure, we ensure that a single element, ker of phi, is mapped to the identity, not several elements. So this means now that our new map from G ker phi to the image of phi is both injective and surjective, making it an isomorphism. And with that, we have finished today's lesson. If you've enjoyed, drop a like, subscribe, and share with anyone who would be interested in this very natural, intuitive subject. I'll see you all on the next time. Have a nice day, and bye.